Hello everyone and thanks for watching Edupedia World videos. In this session of mole concept, we'll start with a new concentration unit called mole fraction. Okay, we'll go into the definition, formula, and then we'll solve some examples to finish up this session. So let's start with the definition part. What is mole fraction? Mole fraction means number of moles of solute present in total moles of solution. Basically, it is the ratio, it is a fraction of moles of one quantity to total moles of solution. Alright, for example, if you have say three different solutions if you have a solution containing three different substances, okay, these are three different substances and their respective moles are given to you. Let's say 1, 2 and 3. Okay, so now I do not care which is solvent and which is solute. Alright, for calculating mole fraction, I can calculate mole fraction with respect to A, with respect to B, or with respect to C. That is, I can calculate mole fraction of each of these substances in the solution. Together, when mixed, they are going to form a solution containing A plus B plus C. Okay, so what will be the total moles of solution? Okay, the total moles of solution will be sum of individual moles, that is 1 plus 2 plus 3. This is what constitutes my solution A, B and C. So if I add their moles, what I get is total moles of my solution, that is 6. Alright, so for calculating mole fraction, what I need is total number of moles and individual moles. Okay, so what will be the mole fraction of A? So mole fraction is represented by letter X. Okay, small x. So XA. Okay, I have written A in the subscript to denote that this is the mole fraction of A. So XA will be ratio of moles of A to total moles of solution. Okay, that is, it is a ratio between individual moles and total moles. That is, XA is equal to 1 by 6. Similarly, for B, XB is equal to 2 divided by 6. That is ratio of 2 and 6, which will come out to be 1 by 3. Okay, and XC is equal to 3 by 6. That is 1 by 2. So this is the mole fraction of A in the solution. This is of B and this is of C. Okay, so this is how mole fraction is calculated. So in words, it is the number of moles of solute or solvent. Alright, doesn't matter, in 1 mole of solution. So what does mole fraction represent? It represents moles of solute in 1 mole of solution. For example, XA is equal to 1 by 6. So this is what this represents, that if I had 6 moles of solution, if my total solution had 6 moles, then out of those 6 mole, 1 mole will be of A. Okay, rest 5 moles will belong to some other substance, which in this case is B and C. So out of 6 mole, only 1 mole is of A. So if instead of 6 moles of solution, I only had 1 mole of solution, then in that case 1 by 6 represents moles of A present in that solution. That is, if I had 1 mole of solution, then out of 1 mole, 1 by 6 mole will belong to A. And rest, what is rest? 1 minus 1 by 6. Okay, 1 is the total moles of solution. Out of that, 1 by 6 is of A. So 1 minus 1 by 6 is 5 by 6. So this 5 by 6 mole of the solution left will belong to B and C. Okay, so this is why we say it is the number of moles in 1 mole of solution. Alright, so mathematically it is very simple to calculate, like we did in this example. Mole fraction is number of moles of solute or solvent, okay, depending on whether you want to calculate mole fraction of solute or solvent or any other substance, divided by total moles of solution. Okay, obviously mole fraction will be defined only for the substance which is present in that solution. Okay, so out of the parts or out of the constituents of the solution, you can calculate mole fraction for any of them. Alright, and if you want to check the dimensions, this is mole. Okay, the above quantity has a unit of mole. The quantity and denominator also has unit of mole. So mole get cancelled. That is, it has no units. It is dimensionless. Okay, mole fraction is a pure number. Alright, it has no dimensions. Okay, so let's note some other points about mole fraction. First, okay, for the first point, okay, first let's focus upon only this part. Alright, forget about this thing. So let's say I have a solution of A and B. Okay, that is only two substances. Okay, my solution contains A, that is say Na moles of A, and let's say Nb moles of B. Alright, so what will be the mole fraction of A? Xa is equal to moles of A divided by total moles. Total moles is Na plus Nb. Alright, total moles of solution is Na plus Nb. And what will be the mole fraction of B? Xb, that is Nb divided by Na plus Nb. Okay, so if I have total moles Na plus Nb and I have individual moles, I can calculate individual mole fraction. I have done that. Now let's sum them up. Okay, let's add Xa and Xb. So what do I get? Na divided by Na plus Nb plus Nb divided by Na plus Nb. Okay, this is what? Na plus Nb divided by Na plus Nb, which is obviously going to be 1. Alright, which is obviously going to be 1. That is why I have written here Xa plus Xb is equal to 1. Alright, why? Because Xa constitute that part of solution occupied by 1A, Xb constitutes that part of solution occupied by B. So if I add them both, they are obviously going to be 1. The sum is going to be 1 because I have added all the constituents of my solution. Alright, so fraction is going to be 1. Okay, Xa and Xb are fractions, so that is mole fraction should always be between 0 and 1. So if I add all the mole fractions, that is mole fractions of all the constituent, what I'll get is 1. Alright, so in general, if instead of just two substances, in general, if my solution is made up of n different substances, alright, then what can I do? I can calculate mole fraction for each of these n substances, x1, x2, x3, x4. Alright, basically I can, let's say x1 I have calculated, then x2 and x3, okay, and so on up to nth substance. Now if I add these mole fractions, okay, these are all fractions, x1, x2, x3, xn, these are all fractions. So this means that they are all going to lie between 0 and 1. Right? So if I add all these x1 plus x2 plus x3 up to xn, then my sum is going to be 1. Okay, I have added the mole fractions of all the constituents. So in that case, I have got mole fraction of the whole of solution, which is obviously 1. That is moles of solution divided by moles of solution. So it is going to be always 1. So in equation, in mathematical terms, okay, it is often written in this form. Okay, sigma obviously represents summation. So okay, summation of xi, where I limit of I goes from 1 to n, range of I is 1 to n. So summation of xi is x1 plus x2 up to xn. So that is always going to be 1, given that my solution is made up of only n different substances. Okay, another thing that we studied here is that xi is a fraction, mole fraction is a fraction, so it is always going to lie between 0 and 1. When will it be 0? Okay, 0 represents that substance is absent, that substance is absent from the solution. Okay, basically there is no sense in calling that a mole fraction is 0. It simply means that substance A or B, basically that particular substance is not present in the solution, so it is meaningless to talk about it at all. Alright, so 0 means substance is absent, whereas 1, what will 1 represent? If mole fraction of certain substance is 1, it means that that is the only substance present in my solution. Only substance present in my solution. That is, what you have is not actually a solution. It is not actually a solution. It is pure substance. For example, let's say I have a container and I tell you that mole fraction of water in this container is 1. So this simply means that the container only has water in it. It does not have salt, sugar or any other substances present inside it. Okay, so rest, for in general, for any case of solution, mole fraction will always lie between 0 and 1. Alright, so we have noted this point, and we have also noted that sum of individual mole fractions, okay, of all the constituents of a solution will always come out to be 1. Okay, once we have figured out these 2 points, let's move on to the next. That mole fraction is independent of temperature. Okay, it is quite obvious. It is a pure number. Alright, it is a pure number because numerator contains mole of one quantity and denominator contains mole of other quantity. And mole is what? Moles represent number of particles, and number of particles in a closed container, number of particles do not get changed by temperature. Alright, we will be talking about closed container as long as it is not mentioned otherwise. Okay, so for a given amount of solution, that is, if you have put a solution into a closed container, then the amount won't change, and if the amount doesn't change, then moles cannot change, and if moles cannot change, then upon changing temperature, mole fraction will not change. So mole fraction is independent of temperature. Okay, last point to note here is interpretation of this mole fraction. Okay, like we studied interpretation of molarity in our last session, let's see how do I interpret mole fraction. Let's take up the previous example. Right, in previous example that we studied in the previous slide, XA came out to be 1 by 6. Alright, 1 by 6. XB came out to be 1 by 3, and XC came out to be 1 by 2. Okay, so how do I interpret this data? Okay, let's say I have 1 by 6, 1 by 3 and 1 by 2 moles of A, B and C. Okay, basically mole fraction represents moles of each quantity in 1 mole of solution. So while interpreting, what I will do is I will assume that total moles of my solution, okay, this data will imply that total moles of my solution, let's say NT, is equal to 1. Once I assume that, I can directly say that moles of A, Na, is 1 by 6, Nb is 1 by 3 and Nc is 1 by 2. Okay, so this is how I interpret my mole fraction data. That is, I can assume that total moles of solution is 1. Alright, I can assume total moles of solution is 1, in which case mole fractions actually become absolute moles of each substance. So XA becomes Na, XB becomes Nb and XC becomes Nc. Alright, this is just a way of interpretation. Alright, and so if you have a question in which XA is this, XB is this and XC is this, so instead of taking mole fractions, you can always assume that total moles is 1. So in which case you get absolute moles of A, B and C. So this makes your calculations easier. Alright, once you know the absolute moles, absolute quantities, you can convert them into mass, volume, whatever is necessary, whatever is required by your question. Alright, but again, this is only an assumption. Technically it is not right. Okay, this interpretation is just a tool for solving questions. For example, if instead of 1 mole, okay, just like we studied in molarity, if instead of 1 mole, if total moles of my solution is 2, let's say NT is equal to 2, then A, B and C, moles of A, B and C will also double. So Na will become 2 by 6, Nb will become 2 by 3, and Nc will become 2 by 2, that is 1. Right? If you will sum them, say 1 by 6 plus 1 by 3 plus 1 by 2, if you add these three quantities, you will see that their sum is equal to 1. Why? Because we have assumed Nt is equal to 1. In this case, Nt is equal to 2. So when you sum this, Nb also becomes twice and Nc also becomes twice, that is 2 by 2. So if you sum 2 by 2, that is 1 plus 2 by 3 plus 2 by 6, what you will get is 2, because we have assumed total moles to be 2. Okay, so this is how you interpret mole fraction data. Okay, if you assume more total moles as 1, you can write absolute moles. Okay, if you assume total moles to be 2, you have to write it this way. Similarly, if you assume total moles to be 3, alright, so instead of 1 by 6, moles will become thrice of this, that is 3 by 6, and B is 3 by 3, and Nc will become 3 by 2. Okay, so let's move ahead and see some examples. Okay, so let's read the question first. I have 1 mole of glucose, 3 mole of sodium chloride, that is NaCl, and 18 gram of water. Okay, I mix them together in a container. So when I mix them, what I am doing is I am forming a solution. Okay, I am forming a solution. Okay, a solution of glucose. Alright, where moles of glucose is 1, moles of NaCl is 3, and moles of water. Okay, I do not have moles of water. What I have is 18 gram of water. Okay, so to calculate mole fraction of glucose and NaCl, what will I do? I'll simply use the formula. Mole fraction of glucose, let's say Xg, will be moles of glucose divided by total moles. Right? And mole fraction of NaCl will be moles of NaCl divided by total moles. So what I have to do is I have to calculate total moles. Total moles N will be Ng plus N NaCl plus NH2O. Okay, so I already know Ng is 1 and N NaCl is 3, but what I do not know is moles of water. Okay, what I have is mass of water. Okay, so it's quite simple to go to moles. We know that moles of a quantity, moles of a substance is given mass divided by gram molar mass. Alright, so moles of water will be, okay, if I want to calculate moles of water will be mass of water, given mass is 18 gram. What is gram molar mass of water? H2O. Hydrogen has atomic mass of 1. Okay, oxygen has atomic mass of 16. So 1 into 2 plus 16, that is 2 plus 16, that is 18. So gram molar mass of water is also 18. So moles of water with me is 1. Alright, so I have calculated that moles of water is 1. So once I calculate this, I can easily calculate total moles. Total moles is Ng plus NaCl plus NH2O, that is 1 plus 3 plus 1, which comes out to be 5. Right, so now I simply substitute the values here in the formula. So mole fraction of glucose is moles of glucose 1 divided by total moles, which is 5. Mole fraction of NaCl, that is sodium chloride, is 3 moles of NaCl divided by total moles, which is 5. So 1 by 5 and 3 by 4. Okay, we can also calculate mole fraction of water, but that is not been asked in the question. Okay, that has not been asked in the question. So we have simply calculated those of glucose and NaCl. Okay, so this answers our question. Right, so you'll see that mole fraction is pretty easy topic. Okay, and it is very important because this concentration unit like molarity is going to be very useful, alright, in all of your topics of physical chemistry. It comes time and again in all the questions. Alright, so in all different topics that you will study, they will often give you data in terms of mole fraction instead of absolute moles. Alright, or instead of volume or mass, they often give you mole fraction, or instead they ask you to calculate mole fraction. Okay, so let's see another example. Following information is available about a certain solution. First, it is a mixture of three different substances. Alright, so first information that we have about a solution is it is a mixture of three different substances. Let's say A, B and C. Next, X1, that is first substance. We have called it A. Okay, say it is 1. So XA or X1 is equal to 0.25. Okay, this is the next information. Then next information about solution is X2 is twice of X3. Right, so X1 is 0.25, B is let's say X2, and C is let's say X3. Okay, so next information is X2 is basically twice of X3, that is 2 times X3. Alright, so we have to calculate possible molar quantities of the constituents. Alright, that is, we have to calculate moles of possible values of moles of A, B and C. Okay, so basically I have to calculate N1, N2 and N3. Let's see. So I have X1. Okay, I have X1, that is 0.25. I have X2 in terms of X3. Okay, let's say I have X2 and I have X3. And to calculate absolute moles, first let's try and calculate value of all the mole fractions. So I already have X1 0.25, but I do not have X2 and X3. Alright, so what I have is two variables, X2 and X3. So to get answers or to solve for two variables, you need at least two different equations. Okay, if you had three variables, we would have needed three different equations. Okay, in this case we have two variables, so I have to eliminate these two variables. So we can easily eliminate X2. Why? Because X2 is twice of X3. So I have eliminated another variable, but I still have X3 as a variable. So I have one variable now, which means I need only one equation to solve the problem. Now where do I get that equation from? Okay, there is no further information available in the question. So what do I do? See, I have used this information. Okay, I have used this information. Okay, I have made use of these two. This I made to eliminate X1. This information I used to eliminate X2. So how do I eliminate X3? I use this information. Alright, this information says that there are only three different substances, that is A, B and C are the only constituents of my solution. Okay, from that I can say that sum of X1, X2 and X3, okay, sum of X1, X2 and X3 is equal to 1. Why? Because these are the only three constituents of my solution. Okay, so I finally have an equation. I have an equation and I have one variable. So I can simply solve that equation to get the value of my variable. So now I have used this information as well. Alright, so you always first look at all the information available in a question and then you try to interpret that information. Okay, once you have done that, you will be left with some missed out parts. Okay, and to solve that missed out parts, either you use mathematical equations or you go through the question again and see what information you haven't used here. Okay, so here I didn't use this information about three different substances, and from that I have developed a mathematical equation which we already know, that sum of mole fractions of all the constituents is always going to be 1. Okay, this is why this equation that we studied today is very important. Alright, because in questions this will never be given to you. that sum of mole fraction is 1. You have to remember it, and it should strike in your mind that, oh, I can use this equation here right now, I have to use it. Alright, so let's solve now. X1 is equal to 0.25, x2 is equal to twice of x3 plus x3 is x3, so this is equal to 1. So I can simply solve 3x3 is equal to 0.75. okay, 0.25 can be taken here, so 1 minus 0.25 is 0.75. so x3 is equal to 0.25. so I have calculated x3. alright, I have calculated x3. so this basically solves our question. How? Let's see. Okay, now I know that x3 is equal to 0.25. this means x2 is twice of x3, that is 2 into 0.25, that is x2 is equal to 0.5, 2 into 0.25, so x2 is equal to 0.5. alright, so this means I have mole fraction of each of the constituents. A has mole fraction of 0.25, B has mole fraction of 0.5, and C has mole fraction of again 0.25. okay, but we do not have to calculate mole fraction. What we have to calculate is molar quantities, possible molar quantities, okay, that is absolute values. So we have to interpret this data. This is mole fraction data, that is, it is in relative terms. Concentration units are always in relative terms, so I have to change this relative data to absolute values. How can I do that? I can simply assume that total moles of my solution is 1. If I assume this total moles of my solution is 1, in that case this mole fractions become absolute values of mole. Na is 0.25, Nb is 0.5, and Nc is 0.25. okay, so this is a possible molar value, 0.25, 0.5 and 0.25, if I assume Nt is equal to 1. Another possible molar quantity, okay, another possible molar values can be obtained by assuming Nt is equal to 2. so since I have doubled the total number of moles, I have to double individual moles as well. so 2 into 0.25 is 0.5, 2 into 0.5 is 1, 2 into 0.25 is again 0.5. okay, similarly Nt is equal to 3. alright, Nt is equal to 3. so in that case I have tripled the number of moles, so possible molar quantity will be 3 times of 0.25. okay, here 3 times of 0.5 and here again 3 times of 0.25. okay, so in general, if total moles are say A, that is A into 1. okay, A is A into 1, so this means total moles of A will be 0.25 times A. okay, total moles of B will be 0.5 times A, that is I have multiplied them by total moles. okay, and this will be 0.25 into A. okay, it's quite simple actually. See, mole fraction is equal to individual moles divided by total moles, individual moles divided by total moles. so this implies individual moles is equal to XA multiplied with N, that is mole fraction multiplied with total moles. okay, so if I assume total moles to be any quantity A, B, C, D, E, F, anything, so my individual moles will also change given same mole fraction. alright, so this is also useful relation, that individual moles is equal to mole fraction multiplied with total moles. okay, but it is quite simple. It has been derived simply from the formula of mole fraction. Mole fraction is individual mole divided by total mole, so individual mole is mole fraction multiplied with total moles. okay, so this finishes up our topic of mole fraction. alright, in the next session we'll start with a new concentration unit. okay, and that should be our last concentration unit, at least for our syllabus, in this case for grade 11th. alright, so until then, and once again thanks for watching Edupedia World videos.